Welcome back. In this lecture, which would be fairly qualitative and descriptive, we'll provide some ways to classify the different types of fuel cell. It gives you a big canvas of options that have been attempted and still being explored extensively. So one way of classifying fuel cell is based on the nature of ion that is getting conducted in the electrolyte. So one of the earliest form of fuel cell that was that got attention extensively was the alkaline fuel cell, because it was used in Apollo space machine in by NASA, wherein it served not only to generate electrical power, but the water from the fuel cell was also used by the astronauts. So in an alkaline fuel cell, OH is the ion that is getting conducted in the electrolyte. You supply hydrogen, uh, and that electrode is at the potential, on the other electrode is at that potential. So if you want to get the thermodynamic voltage that can be obtained from the fuel cell, EC minus EA, which would be around, let's say 1.23. Okay, that's the just based on thermodynamics. So another common configuration is when the electrolyte conducts proton. So these are all called polymer exchange membrane fuel cell or proton exchange membrane fuel cell. The proton is the nature of the ion that is getting conducted in the electrolyte. Again, this voltage is around 1.23, the thermodynamic voltage. So as opposed to these cell potentials, are quite different, okay, because that is dependent upon the nature of the reaction that is being undertaken in the fuel cell. These refer to the equilibrium cell potentials, along with the different Faraday reaction. The equilibrium cell potential also, half cell potential, will also change. So other option is an electrolyte that conducts O2 minus, as opposed to these two reactions which operate at relatively low temperature, let's say below 100 degrees, below 90 degrees centigrade. This operate at fairly high temperature. Okay, this might be even 600 to 800 degrees centigrade. So one of the reasons why this configuration, so-called solid oxide fuel cell, is an important approach to fuel cell, is because the kinetics of oxygen reduction becomes simplified at higher temperature. If you want to increase kinetics, one way of doing that is via having high temperatures. So in these cases, you may still increase the kinetics by using very electrocatalysts, which involve noble metals. Precious metals are utilized for electrocatalysis of oxygen reduction, which significantly increases the cost. In solid oxide fuel cell, you may end up using uh, elements that are not that expensive. Inexpensive materials are utilized, and you have the advantage of using higher temperature, but that also comes with its own challenges we will look at as we progress. So another way of classifying um, the fuel cell is also correlated with the temperature of operation. A direct methanol fuel cell, which we introduced in the previous lecture, has been utilized for portable power. You have um, direct methanol fuel cell powering laptops. Okay, so this has been attempted. The operating voltage is this much. The membrane and electrocatalyst can be expensive, and the membrane utilized is same as what is used in a PEM FC. This is the proton exchange membrane fuel cell or polymer exchange membrane fuel cell. So this is being considered in many contexts. For example, even in India, now how to use these PEMFC in buses has been demonstrated, but Europe has demonstrated it to a much greater extent. Um, this is surely a competitive configuration. The operational voltage is somewhere between 60 to 90. Um, as opposed to, let's say, an alkaline fuel cell, which is susceptible to carbon dioxide poisoning when you use air. PEMFC is not susceptible to carbon dioxide poisoning, but this has other challenges, requires precious electro catalysts, fairly expensive electrocatalysts. Because the temperature of operation is not that high, it may provide rapid startup and shutdown. The fuel cell can be started up very quickly, and it can also be shut down very quickly, like what you have in a battery. There is this alkaline fuel cell, which is susceptible to carbon dioxide poisoning because of the alkaline nature of the electrolyte. Its operational temperature is slightly higher than PEMFC, requires pure hydrogen, but it has the advantage of not having the need to use precious electrocatalyst. Okay, so that is, see, as soon as you have acidic medium, the problems of corrosion becomes fairly challenging. So to resist corrosion, you may end up using non-noble metal, I mean, noble metal catalyst. Alkaline fuel cell, you may have the option of using non-noble metal electrocatalyst. Phosphoric acid fuel cell has an interesting temperature range. Okay, this is not too high that you would see in solid oxide fuel cell. It is also not too low. So one way to increase the kinetics is having high temperature. This has been considered for stationary uh, electrical power generation. It typically operates on reformed fuel cell. It may have long life. What do we mean by cogeneration here is that there are two ways to generate power. Obviously, from a fuel cell, we want to get electrical power. In addition to electrical power, the exhaust of a fuel cell, let's say water vapor, can be at a high temperature that itself might be utilized for getting power power and energy conversion by thermal means. Okay, so this has been most extensively demonstrated in the context of solid oxide fuel cell. We will look at that in a minute. You have molten carbonate fuel cell that operates at much higher temperature. Again, stationary power sources, it has been explored as the option of high efficiency and good cogeneration. Cogeneration has been most extensively utilized in solid or demonstrated in solid oxide fuel cell. You here look at the operational temperature. This is one of the significant challenge. So when you have a fuel cell operating at this temperature, the electrolyte and the entire fuel cell has significant thermal mass. The heat capacity is fairly high. So the sensible heat required to increase the temperature, let's say from room temperature to this temperature, that itself is a challenge. And you cannot rapidly increase the temperature because a rapid increase in temperature will introduce thermal stresses within the fuel cell. So you have to gradually increase the temperature. So this feature has to be contrasted with this rapid startup and shutdown in a PEMFC. So here, if you want to start a solid oxide fuel cell, you have to do it gradually because the temperature is increased gradually. And the shutdown has to be done in a gradual manner. So once the fuel cell is operated as begun operation, you want to keep it running. That can be done by continuous supply of the fuel. But it has other advantage. One is that solid oxide fuel cell is fairly efficient, and another big advantage is cogeneration. That is, the water vapor that is coming from a solid oxide fuel cell is at a very high temperature. At this temperature, if that water vapor is supplied to a turbine, then the turbine can give rise to power, right? So just like an typical thermal power plant, you can have two ways of generating power. One is electrical power directly from an SOFC, and also power from this water vapor that is available at a high temperature. But utilizing high temperature has significant material challenges, and this shutdown and startup is another big challenge in an SOFC. But there are companies that have been exploring both the commercialization of PEMFC. There are many companies that has been attempting this, and there are some other companies that have been attempting SOFC. So, especially for transportation systems, PEMFC looks like a good option. In terms of stationary power generation using SOFC, using fuel cell, SOFC looks like a good option. Note, there are two big advantages, right? One is there is no Carnot limitation, and in addition, fuel cell is like a flow reactor, as opposed to the batch reactor form of a battery. As long as you keep supplying fuel, you can keep on generating power efficiently. So the dream of extensive use of fuel cells as an energy conversion strategy has never faded away in the last, let's say, 100 years. So, but still, much of the challenges remain. In the next lecture, we will look at this important feature, especially from an electrochemical engineering perspective, how to rationalize the current voltage IV characteristics of a fuel cell is very critical. These are called polarization curves. We will discuss them in the next lecture. Thank you.